Hi, everybody. So, in this video, I'll be briefly touching some very important concepts of operating system. So, people who have not taken up a course in operating system might find it useful. So, let's get started. So, the first thing to understand is that the system operates either in user mode or in kernel mode. And this idea is actually mapped at hardware level. And by that, I mean that in hardware, actually, there is a flag which is set and which indicates whether currently whether the system is running in user mode or if it is running in kernel mode. And so, why do we need these two modes? So, the answer is straightforward. When the system runs in user mode, then the uh, program actually has lesser privileges. And when the system is running in kernel mode, then the current program has high privileges. And by high privileges, you mean more instructions can be executed, instructions which cannot be executed in user mode. So, of course, it is for security reasons. So, and to give sense of what these privileged instructions are, like things like access to hardware, polling hardware for data, this is something that cannot be done in user mode. It is done in kernel mode. So the first question you should ask is, but I write code which reads data from file system or reads data from network socket all the time. So how does that happen? Right? Because my program doesn't run in, so I'm the one who's writing the program, not the kernel. So the answer is straightforward. Kernel provides something called system calls for user programs. So when user program has to access anything related to hardware data or anything, then it actually calls these system calls. And the way things happen is, so when the user program makes a call to these system calls with right set of arguments, the system toggles from user mode to kernel mode, and the control moves to kernel. Now the kernel is the one which actually executes the system calls, interacts with the hardware, and makes this whatever data it has to provide. It makes all that data available to the user program. So we've understood a couple of things. We've understood the two modes in which the system runs. We have seen what a system calls, and we've also seen in the one scenario in which how the system shifts from user mode to kernel mode. That is by invocation of system call. Now we'll move to another very interesting topic, which is hardware interrupt. So the thing is that every hardware, every device has this innate capability to raise what is called as hardware interrupt. So this is a way by which the device informs the CPU that look, I have something to say, right? So it creates some kind of buzz in the hardware circuitry. At a very crude level, you can understand that, let's say there is a wire which connects this device to the CPU, and whenever the device puts one into this wire, the CPU is signaled that, okay, this device has something to tell me. So the device, meaning that the device has raised a hardware interrupt. And then the CPU can take it upon, and then the CPU can decide how to handle that interrupt. So now we will see, third thing is we will see a very practical use case of this hardware interrupt, right? So to understand that, first let's understand one problem and then let's see how this hardware interrupt actually solves this problem. So the problem is, how does context switching happen? So before we get into that, we need to understand a couple of things. We need to understand what is a context, what is a context switching, why is this needed, and then we'll move to how that happens, right? So context is, so let's say a program is running in the system, and context of that program is actually the state of the program. And so it's a very like deep topic. I'll not be able to cover everything, but at a very logical sense, you can understand that the state of the program is what? It is the current line, um, the current code line, right? The current uh, line which is being executed, so which is being captured in instruction pointer register. So the current code line and then the values of all variables, the call stack, so which method is being executed and so on, right? So at a very conceptual level, context is all the information which captures the state of the program. So that is the context. Now, what is context switching? Context switching is when this CPU has to be allocated. So we can have multiple programs running, right, in the system. So the way it happens at one time, of course, one program is running. So what has to happen is that the CPU needs to be allotted from one program to another, and so on and so forth, right? So there are n number of programs running. The CPU has to rotate between all these n programs. So context switching is the allocation of CPU from one program to another program. So that is context switching. And why we need it? Because obviously we want all the programs to have their share of CPU so that they can all run. And how it happens. So that is interesting because a user program is running in the system in user mode, and obviously it will not be willing to relinquish the CPU. Somebody has to snatch the CPU from it, and it's not executing any system call, so the control never comes in kernel mode. So the program is happily has all the system, and the program is happily running. So now comes the role of a timer. So timer is a very interesting hardware, and a bit undervalued hardware in the sense that we often talk about disk, we talk about SSD, we talk about network socket, we talk about keyboard, mouse. We don't talk so much about timer. So timer is the one which comes very handy at multiple times. So what happens is before this user program is running, the kernel actually configures this timer and tells boss, you um, raise the hardware interrupt after, let's say, 5 seconds. Of course, things don't happen at second level, they happen at nanosecond level. But for an example, so the kernel has actually, before this user program runs, the kernel actually configures the timer to start to raise the hardware interrupt after 5 seconds, right? So now the user program is running, the timer after 5 seconds raises hardware interrupt, control comes to CPU. Now, when control comes to CPU, the first thing it does couple of things. The context of the user program is saved. The hardware flag in this hardware flag toggles from user mode to kernel mode, and context of the kernel is loaded now. So the instruction pointer now points to a coded kernel, right? Good. So far, so good. Now the control has come to the kernel. Now, the kernel has all the bookkeeping, has all the data structures, has all the bookkeeping. It knows all the threads which are running in the system. So now so it's logical, right? So now if the kernel has access to all the bookkeeping, it can very well decide which user thread on whatever criteria it wants to give the CPU next, right? So it handpicks a next user thread, and then what it does is it actually then toggles the some using some instruction. It toggles the so it loads the next user program context, and it toggles the mode flag from kernel to CPU. And before that, it also configures a timer that again interrupt after, let's say, 5 seconds. Right. So now what we have here is the control actually has moved to the next user program, and the mode flag is set as user mode, and timer is also configured. So now the cycle will keep on rotating, and this is how the context switching happens. So we've seen a couple of things. We've seen how hardware interrupt happens. We've seen in a practical use case where timer hardware interrupt actually helps in context switching. So that's all for now. Thanks, everybody.